In my last lecture, we talked about different kind of sensors, and you have analog sensors, which mostly will give out a voltage that is proportional to the measurement or the quantity of the changes in whatever you want to measure. Sometimes they may give you a resistance change, like a strain gauge, but then you can actually feed a voltage or current through to give you a voltage change. Sometimes the signals may be small, then you need to amplify, which we'll discuss later. Sometimes they may give you a bias, like a strain gauge. Strain gauge will have a nominal resistance, and then the resistance will change with the level of stress it will be under when you glue the strain gauge onto a surface. And of course, that change is quite small. The nominal resistance can be quite high. So, and if you inject the current through, then you will get a nominal voltage even when you don't have any stress, or the object is not under any stress. And so you need to get rid of that nominal voltage. Now this circuit here is a way to get rid of that nominal voltage. Okay, the circuit consists of, if we look at the general principle of that circuit, this is called Wheatstone bridge, and it consists of 4 resistors. Now, sometimes we use strain gauges to replace resistors, but for the time being, just consider these 4 all standard resistors. Now, if it is formed in this particular way, but if you look at closely, these two, R1 and R2, are connected in series. R3 and R4 are connected in series. Then the 2 branches or 2 necks are connected in parallel. That overall supply is come from external. So you supply a voltage to that circuit and keep the voltage as constant as you can. Okay, so Vs is the input voltage applied to the circuit. That should be kept as constant. Now, the voltage applied to both necks, so the current going through R1, R2, that's one branch. The same voltage will go through R3 and R4, that's another branch. So the voltage, the potential at this point there, will be Vs divided by R1 and R2, that will give you current, times R2 will give you the voltage between this point and the reference point at the bottom. The voltage at this point will equal to input voltage divided by R3 times R4. Multiply that by R4, that will give you a voltage at this point and to the reference. But the voltage between the point there and the point there is a difference between 2. Therefore, the overall output, if you connect this point out, then the overall output voltage VO equals to R2 divided by R1 plus R2 times Vs minus R4 over R3 plus R4 times Vs. Okay, so that will give you the output voltage. Now, circuit like that, when you have all 4 resistors to have the same resistance value, say they all equal to some Rg as a nominal voltage, then this becomes Rg, this is Rg, this is Rg, so Rg over 2Rg, that's 1 over 2. This is Rg, this is Rg, and this is Rg, so Rg over 2Rg, that it also equals to 1 over 2. So 1 over 2 minus 1 over 2, that's 0. So under normal condition, when there is no strain applied, then the output will be 0. So this way we'll get rid of the bias. Okay. Now, how that can be used to measure the strain or measure the stress a surface under. Say, for example, we can use this circuit and replace one of the resistors with a strain gauge. Okay, and in this case, say my R2, I replace this resistor with a strain gauge. All the other resistors, R1, R3, and R4, are standard resistors, but they will have the same value as the resistance of the strain gauge under normal condition, under nominal condition, when there is no strain. Okay, so when this strain gauge is under no stress, then four resistance will be the same. And of course, when the four resistors are the same, the output will be equal to 0. But say suppose you glue this strain gauge onto a surface, and surface is under some kind of strain, and it's actually bended a little bit, then the resistance in that strain gauge will change. It can change either way. It can be positive, it can be negative. Depends which way the surface is bending. Say it's positive, for example. Okay, so the resistance here for the R2 or for the strain gauge will equal to Rg plus some delta R. Okay, delta R is how much it changed due to the stress. Okay, all the other resistors R1, R3, and R4 all equals to Rg. That's the resistance of the strain gauge in the nominal condition. So these R1, R3, and R4 will not change, either because they are resistors or they are strain gauges that are not glued on the surface, so they are not affected by the shape of a surface that's under strain. Okay, so substitute R2, R1, R3, and R4 into that equation, and what we will get is this. So I'm going to replace R2 with Rg plus delta R, R2 with delta R plus delta, Rg times plus delta R, all the resistors with Rg. Second part of that equation 1 will become Rg over 2Rg, so it's over 1 over 2, that's 1 over 2. First term in equation 1, the top becomes Rg plus delta R, that's because that's R2. The bottom, the denominator term, becomes Rg plus another Rg plus delta R, so it's 2Rg plus delta R. Now I'm going to take this half out, and of course when I take this half out of bracket, I need to take half out as well, so I need to add a 2 here, add 2 there. Okay, so if you multiply 1 over 2 back into the bracket, you get back to equation number 4. Now reorganize that. This is a 1, therefore you can actually find the common denominator. So on this term becomes 2Rg plus delta R over 2Rg plus delta R. Okay, therefore you can subtract the two terms. This will give you delta R over 2Rg plus delta R, and then times Vs. That's the voltage you supply to the circuit. Now when you get here, think about comparatively between the nominal resistance and the change of resistance due to strain. Now Rg typically will be in the range of 400, 500, or even 600 ohms. Delta R will be less than 1 ohm most of the time, even under the full design stress. So relatively speaking, when you compare these two terms, 2Rg is a much larger than delta R. Therefore, I can approximately neglect that delta R at the bottom. So this approximately equals to 1 over 2 times delta R over 2Rg. So combine the two together, I'll get 1 over 4, and then times Vs. Now, if you look at that equation number 7, under nominal condition, when there is no stress, delta R, then there will be no change to resistance. Therefore, delta R equal to 0. So no stress, the output voltage, VO, will equal to 0. If the resistance increases, that will to give you a positive delta R. Then you will have a positive output proportional to the input voltage. If delta R reduces, that will give you a negative delta R. Then you will get a negative voltage that is proportional to the input. Okay, and of course that's delta R is proportional to the level of stress the strain gauge is under, and Vs is constant, so the only variable in here is delta R. So therefore you can consider the output will be proportional to the resistance. And now is a voltage that we can deal with. It may be small, it's probably in the millivolts. It's not in the best range for computers to take. Computers like a bit higher, like the voltage a bit higher. But we can actually do something else about that later. However, there's a problem with this arrangement where you only use one strain gauge in the circuit. That is, the resistance of a strain gauge vary with temperature as well. Not only they change with the stress, they also change with temperature. So if the temperature of the surface you try to measure changes, even without the strain, that delta R will change. Delta R change, that means your voltage will change. So your computer is not that clever, and it can't really tell the difference. So what will happen there is that, say for example, we have an extra component here for the strain gauge, this delta RT, which is due to the changes in temperature. Then of course your output will have a delta RT as well. And without delta R, you will stay output. That will get very confusing. And of course there are ways to deal with that, but we can actually use the strain gauges themselves to overcome this problem. Okay, for example, we can use two strain gauges. Now I'm going to use two strain gauges this time. I'm going to put a strain gauge to replace R1. I'm going to use another strain gauge to replace R2. R3 and R4 will still be the standard resistance. The resistance of all four devices will have the same value when the strain gauges are not under strain, i.e. the surface of the where you glue the strain gauges onto are not bending. Okay. Now the way I do it, or the way it can be done, is you put one strain gauge to one side of the surface you try to measure, and you put the second strain gauge onto the opposite side of the surface you try to measure. Therefore, when it's bending, one resistance will increase, the other one will reduce, and vice versa. R3 and R4 will remain constant. So, for example, I say R2 will increase with the strain or with the bending. R1 will reduce with the bending, so I get a plus delta R minus delta R there. Now, if I replace everything back into this equation, R2, R1 into there, R3 and R4 into there, I get this. And even consider the resistance changes as well. So I added resistance changes to R1 and R2, which are my strain gauges. Okay, now look at the difference here in equation 2 and equation 3. Delta R is due to the stress or due to the bending of the surface. One will go up, the other one is go down. But the change is due to temperature, because the same object, same environment, so they will both, either they both go up or both go down. So although for delta R, it's one is plus, one is minus, but for delta RT, this is the component due to the temperature change. Both will be positive or both will be negative. So if I put everything here into equation 1, and I end up, so there's a bit of math here. So if you are patient enough to go through the steps, okay, and you will see why I've done this in this way. But I'll leave that for you to do. What we end up is this. We will end up, it says voltage will equal to 1/2 bracket delta R over Rg plus delta RT. Now delta R disappears at the bottom. Only the delta RT left. Now, relatively speaking, between Rg, this is a nominal value, and delta RT, delta Rg is much greater. So therefore, we can actually neglect that one. So approximately, output equals to 1/2 delta R over Rg times S. Now, if you look at this equation, number 4, the only variable here is delta R. Delta R is proportional to the level of the stress of the surface where you mount your strain gauges onto. So therefore, your output voltage is proportional to the level of stress you're trying to measure. So not only the effect of temperature is removed, because we use 2 strain gauges and we arrange the strain gauge in such a way one resistance will go up, the other one will go down. But also, the output voltage will be doubled. Now, in the previous case, this is 1/4. Okay? But in this case, it's 1/2. So it's double the output. We can actually do better even than that. And in most applications, people will use 4 strain gauges. So there will not be any standard resistors. Now, because the strain gauges are cheap, they are very easy to make, they're fairly cheap, so they're not going to be a lot more expensive than the resistors. So we use 4 strain gauges, no resistors needed, and therefore, we arrange them in such a way, R2 and R3 on the one side of the surface, R1 and R4 on the other side of the surface. So when the object is bending, R2 and R3, if R2 and R3 have the resistance increased, then the resistance of R1 and R4 will reduce. So therefore, one is plus delta R, the other one is minus delta R. Okay, we can prove that this kind of arrangement will not have any effect of the temperature as well. So I added 2 terms here, plus delta RT and plus delta RT. Again, resistance change due to temperature will either go up or go down for all strain gauges together. Okay, so substitute equation 2 and equation 3 into equation 1, and I end up with this. So output will equal to delta R over Rg times Vs. Again, Rg is the nominal resistance. That's the resistance of the strain gauges under no strain at all. Vs is the input, which is a constant. The only variable here is delta R. So you can see here, output voltage is proportional to resistance change, and therefore is proportional to the level of stress. And of course, that voltage is still quite small. Again, we are talking about a millivolts, and it's out of the range that computer will like. But it is, again, it's double the output when you use 2 strain gauges. It's 4 times as high as when you use a single strain gauge. Okay, and critically, the reason we are, the main reason is try to actually remove the effect of temperature change rather than getting a higher voltage, because we have other ways to deal with the lower voltage. Okay, so I skipped some maths, and although I've actually put some there in my derivations there on my slides, but I would like you to actually do some practice there, use strain gauges and how they are not affected by temperature, that kind of stuff. So you can see the practical question explains itself. Okay, if you want to do other options, and in this question, I changed the arrangement slightly differently to my example. Okay, just to give you a chance to practice. But I'd like to carry on with the rest of the discussion on how to deal with output from the sensors. Okay, so strain gauges, we can use Wheatstone bridge to remove the bias. But most sensors, analog sensors, will give you a voltage that is quite small. And it's out of range that computer like. Computer like, typically computer like a voltage between, say, several volts or positive or minus, but it is within certain range, several volts rather than millivolts. And so normally we would have to connect a circuit after the sensors. Okay, so you feed the sensors, the output from the sensor, into something called an amplifier. Now, amplifier is a circuit that we use op-amps as a device. This is a little op-amp device. It's quite small, but it's very useful. Now, the characteristic of an op-amp is that the input resistance or impedance between V positive, V negative will be infinite. And current goes in is 0. The voltage difference between V plus and V minus is 0. Okay, so there is no potential difference. The resistance is high, and the gain of that in open loop is very high as well. So the way to use it is to form a circuit like that. So in the middle is my op-amp. This is a negative input, this is positive input. And a simple amplifier will look like that. This is your input, this is the voltage that you feed from your sensor, which is very small, millivolts, or even microvolts. This is the output that probably will be connected to the computer or computer interface. If you look at this circuit, the positive side of the op-amp is connected to the ground, the reference point. But we said earlier, the potential difference between positive and negative is 0, or can be considered as 0, it is so small. So therefore, the potential at this point, this particular point there, is also 0. Okay, because it's connected to the ground. The current going through this resistor will be Vs minus 0 divided by R1. The current going through R2 will be 0 minus VO divided by R2. Now, because the property of the op-amp is such that it doesn't take any current in. If there's no current going there, then the current going through R1 will equal to the current going through R2. So R1 equals to RI2, and if you equate the right-hand side of the two equations together, you get that. So VO equals to minus R2 over R1 times Vs. Vs is the input that's fed from the sensor. I can choose a R2 value that is many times higher than R1. Okay, so the ratio will be higher. Therefore, the output voltage will be much higher than the input. That's a way to actually increase the level of voltage from a sensor, so that before the computer can take it. Okay, now you will notice there's a minus sign there, but it really doesn't matter. As long as your computer knows it's reversed, it doesn't matter. Or if you want to get rid of that sign, you can actually connect another similar circuit to there to reverse the sign. But that's not the problem. The issue here is I try to use R2 over R1, select the values of R1 and R2 to give you a high ratio, therefore to give you a high gain. Okay, so your voltage, say if my voltage is from the sensor is from 0 to 5 millivolts, I want to increase that to 0 to 5 volts. Therefore, your gain would have to be 1,000. So R2 would have to be 1,000 times larger than R1. Or if your input is 50 millivolts, or if your input is 10 volts, 10 millivolts, and you want output voltage of 1 volt, then you need a gain of 100 times. Okay, so from 10 millivolts to 1 volt. 1 volt is 1,000 millivolts. So you will need a gain of 100. Therefore, R2 will be 100 times larger than R1. So that's your design. That's basically depends on what your requirement is. Sometimes we also use something called differential amplifier. It is still based on the same op-amp, but we use 4 resistors. But these two would be the same. These two would be the same. Now, in this case, the math is, again, the derivations are given on the right-hand side, but the message I really try to emphasize is this, is that the output voltage will be will equal to R2 over R1, V2 minus V1. So you could potentially have 2 inputs, and then you want to work out the difference. Or you have an input that is not sharing the same ground as the rest of the circuit. So the negative part of the input is cannot be connected to this point. Okay, in this case, you will need a differential amplifier. And again, if you want, you can select the R2 and R values to give you the ratio you need. Normally, this ratio is not higher than 1. So your output will be a lot higher than the input. You are basically making them larger, so that's why we call them amplifiers. So you get them into that range, into the range that computer like, or other digital circuits like. And often you also need to use filters, because sensors can carry noises, or sometimes it only has a working range within a certain frequency range. Okay, all the other input from other frequencies are not really the real reflection of the quantity that you want to measure. So use all sorts of sensors. There are different types of sensors, and again, we don't have that much time to look at each individual ones. But this list just give you awareness. There are different sensors like low-pass filters, which will net the lower frequency component goes through, but stop the high frequency noises. Okay, so at output, you won't see the noises, or you see lesser noises, like what we use for anti-aliasing in the sampling process. And then you have high frequency, high pass filters, where it will net high frequency components to go through, but stop low frequency ones, like drift. Some sensors have a small drift, and if you don't need low frequency measurement, then you can use a high pass filter. Band pass nets a particular range of frequency goes through, so it stops the high and low, but net the frequency component in the middle goes through. And then there's also band stop, or sometimes called notch filters, which is opposite to the band pass filter. So it stops the frequency in the middle range, nets the lower frequency and high frequency components to go through. They are used for different applications, but depends what applications are. So, but it's important that you are aware of different filters that exist. So that's amplification, that's filtering. And then you get to the point where you are ready to convert the amplified signals. So the sensors from the signals will be amplified to the level that computers like. But again, you're still talking about volts. Computers like 0 and 1s. Okay, they don't like volts. So we need to convert the voltage into 0 and 1s. So on here, we will need more than one channel to represent digital, because digital, each channel only have two values, 0 and 1. But you need multiple channels to form a high number. Okay, and of course, the opposite to the A to D converter, as I said in my introduction for digital system, you also have digital to analog conversion. So you're basically going backwards to say, right, these are the numbers, 0 and 1s, I need to convert that back to the voltage. The process is reversed, but the principle is very similar. So we're really just going to talk about the analog to digital conversion process. What happens here is you have a range of input that you expect from the sensors after amplification, after the filtering. Okay, say for example, it changes. I know the maximum within my measurement range. This voltage now will change from 0 to 5 volts, and I need to convert that into 0 and 1s. Depends on how many channels or how many bits I use or how many digits I use. I need to convert this into 0 and 1s. That covers the whole range. So it's important to understand these 0 and 1s. Okay, so I use this slide to make a point there. Say my A to D converter will have 4 digits. Okay, 4 channels, 4 0 and 1s. In combination, I use all 4. If I use all 4, this is really what's in the binary numbers. If I have all 4, put them together, if they're all 0, that represents 0. If 3 of them is 0, say B1, B2, B3 are 0, this B0 is 1, that represents 1. If B1 is 0, B1 is 1, the other 3 are zeros, then that represents 2. If B1 and B0 are 1, B2 and B3 are zeros, that represents another number of 3. You can go on, change the numbers, change where the ones appear or ones zeros appear. You have 16 possible numbers with 4-digit binary numbers. Okay, 4 binary numbers will give you 16 possible decimal numbers from 0 to 15. So that's from 0 to 15. Why 15 there? 15 is 2 power of 4. 4 is number of digits we use. So a total of 16. But it is starting from 0 to 15, not to 16. So there are 16 of them. So basically, if you convert 0 to 5 volts, it will divide 0 to 5 volts into 16 different parts. Okay, each number will represent a voltage range. Okay, but of course, often we need more than that. 16 numbers are not enough to represent them. Now, in the olden days, 4 digits were possible. They were used because the technology was not that advanced. But nowadays, you don't even see 8 digits. You often see a lot higher than that. But I use 8 digits to represent this. This diagram actually shows, again, just a different way of interpret this pair slide. So say my input range is from the minimum, V minimum, to V maximum. So minimum value is there, maximum value is there. Now I use 8 digits this time. 8 digits will have 2 to the power of 8. That's 256 minus 1. So the maximum number was 255. The minimum number was 0. Okay, so there are 256 different numbers. Now to convert your input, A to D converter is a device that converts the minimum voltage to 0, maximum voltage to 255. Feed that into a computer. What's in between? That's divide that voltage by 256. Okay, so I can divide this by 256. So the maximum error, therefore, because you can't do anything better than 256 divisions. So that you get error. So some voltage very close to each other will get the same number. Therefore, the maximum error can be calculated using this formula. So it's range, maximum minus minimum voltage, divided by 250. That's the resolution of an A to D converter, or the measurement error. The measurement error because of the A to D conversion process. 10-digit digits will do better. Okay, the error will be range divided by 1024, because you have 1024 different numbers. 12-digit will be the error will be the range divided by 4096. Sorry, this should be 4095. The maximum number is not 5. Let me just change that number. There are 4096 different numbers, but because it's a 12-digit, therefore it's a 2 power of 12, and the largest number is 4095. That's 2 power of 12 minus 1. So the resolution will be a lot better, or the error will be a lot smaller than the 8-digit. Okay, or the 4-digit will be even worse. Okay, so it really depends on how many channels we use, or how many digits we use to convert the analog signal. And if you want better resolution, smaller conversion error, then you need more digits there. Okay, so then our computer gets zeros and ones, but inside the computer, you have to write your program to say, right, this 255 actually represent what volts, and if the number is 128, you know it's in the middle, that it represents halfway between the two voltages. If it's somewhere a quarter there, that's quarter there. So if it's 64, that will be a quarter of the range. So you will know, as a software engineer, you will know what these digits number, at least 0 and 1 represent. So that converts into A to D. And of course, nowadays, because the computers are so powerful, we don't use a computer just to do one measurement. Often we use a computer to take in a lot more measurements and convert analog signals, and you also send analog signal out through D2A converters. Now, if you have digital sensors like position encoders, and that's different kind of interface you require, because now we don't need to amplify it because we get 0 and 1s. We don't need to filter because there are no noises, but you need to take them bit by bit through a different kind of interface called I/O port. And if you get into a computer, then you will know what the I/O ports are. And they only take two kind of signals. One is 0, the other one is 1. Okay, so there is no mix-up. Also, when you feed your signals into a computer, and you can do it in two different ways. You can either send all zeros and ones into a computer in parallel form. So all the zeros, it doesn't really matter how many digits you use. All the 0 1s will go in from the A to D converter onto the computer at the same time. Or you can feed them one by one. So you start from, you send. So if you have 4 numbers, for example, parallel will send all 4 in at the same time. But also you can send this 0 first, and then send 1 next, send 0 there, and send there. In this case, you only need one channel. but slower because it has to take turns. So there are different ways, but we are not really computer engineers here. And I really just want you to be aware of what's going on or what might happen. So when you really get to the point that you need to implement a controller and that you don't get lost. Okay, so there are different ways of doing things. Each of the topics I've been through here will need a lot of more detailed study before you become an expert. So there's quite a lot of things to learn if you're ever going to use computers to implement digital control systems. Okay, and again, that's another thing, but I'm going to go skip through that because it just shows you the typical arrangement from the sensor to A to D converter. That's the bridge, the amplifier, the filters, things like that. I've gone through that before, so I just skip that. And this is your practical question. And again, there's a range of questions. I try different parts of the topics that I covered. So I'm not really to have a go at it. But I'm here for your tutorial session if you have any questions. Okay, see you in a bit.